Hi students, it's Ross, your TA. Now I've gotten a lot of questions on how to do longest prefix matching for IP addresses, and in particular, how to do these problems where, given a routing table, simplify it. So I wanted to walk through this in a bit more detail, do a couple of examples, and give you some tips on how to go about solving these problems. So first, imagine that we are in a universe where all IP addresses are only 3 bits long. So we can express every possible destination with only 3 bits. Now, to give a little background, as you know, routers, their goal is to figure out how to get packets through the network. And that happens in 2 parts. So first, the router has to decide what its paths are to get to every destination. And it does that by computing this routing table, which is just a set of rules that lets that router say, given a packet, where do I need to send this packet to get it to the destination? And then once it has that routing table, then that router is going to be receiving hundreds and hundreds of packets all the time. And for every one of those packets, it needs to look at that packet's header, its destination address, and based on that, figure out where to send that packet. So to give an example, let's say that this router that's already computed its routing table receives some packet that has an address 101. All right. Now, the router needs to figure out where to send this packet with that address. So one naive way you could do this is for every one of these rules, check it against that packet to see if it matches. So we could take, let's say, the first rule and ask, does it match the address 101? And so we can look and see that the first digit in this rule is a 0, the first digit of the packet's destination is a 1, so obviously these rules don't match. Okay, and we can do this for every rule. For every rule, we can compare that packet's IP address to the address in the rule to figure out where to send it. But in order to check that for every single one of these rules, it's going to take a long time. It's not very efficient, right? And when a router has to be doing this for thousands of packets all the time, constantly, we need to be more efficient than that. That's not going to cut it in today's internet. So what we do is we use some nice data structures that make computing which port to send a packet out a whole lot faster. Now, in real life, routers use all kinds of crazy optimized hardware and data structures, but in this class, we'll be discussing them in terms of binary trees, which are pretty simple data structure, but also pretty powerful, as we'll see. So this tree represents all the possible addresses in this network, right? Since we only have 3 bits in the universe, this tree can represent all possible bits. It has 3 levels. So to make the process more efficient, we use this tree. And so what the router does in advance, before it receives any packets, once it has its routing table here, what the router will do is it will take that routing table and insert its information into this tree. So we'll take the rule 0, 1, star. Okay? So what the router will do when it receives a packet is it's going to start at the top of this tree, and it's going to walk down the tree in either direction based on what the bit of the packet's address is. And by walking down the tree, it will be able to determine which port it should send that packet out. So first we need to add the rules to the tree. So let's start with 0, 1, star. So we'll start at the very top, and we'll just go down to 0, 1, and then the star is a wildcard. It means that this bit could either be a 0 or a 1. So what that would look like in this tree is at the point 0, 1, at this node here, if a packet matches this rule, then we should send it out port 2. So I'll write port 2 here. Okay? By the way, this is not the discussion from, or this is not the problem from the discussion. I'll cover that later in the video. For now, this is an example problem that I've made up. So let's continue marking these routes on the tree. So we'll take the next route, 0, 0, 0. So that would correspond to 0, 0, 0, this node down here. So we'll mark this node as port 1. Right? Take the next one, 0, 0, 1. That is port 1. Next rule is 1 star star. So that is 1, and then anything we match past this point, we would send it out port 1. That's what this rule says. So we'll mark port 1 here. Okay? And then the last rule, 1 0 star. So that is 1 0 star here, and we'll send it out port 2. Okay? So this is what our tree looks like once we've taken all of the data in the routing table and inserted it into the tree. Now let's walk through what happens when that router receives a packet now and it needs to decide which rule it matches so it can figure out where to send that packet. So let's start with our example packet 101. So what the router does is it will take this IP address that's in the packet and it will start walking down the tree with that IP address. And while it's doing this, we're going to keep track of what the last match we've found is. So I'll write last match here. Okay, so let's start. So in the beginning, the first bit is a 1. So that means we'll travel down to this node, 1. Okay? Now, at this node, we have a rule that matches. This rule says that if you have an address which matches 1, and then whatever comes after it, you send it out port 1. So what we'll do is we'll keep track of the fact that we've reached this rule. So we'll say that the last match we found is port 1. And that corresponds to 1 star star. Alright? But we'll keep walking down the tree. We're not done yet. So the second bit is a 0, so we'll come to this point. Now this node has a rule that matches port 2. So if you have a packet that matches 1 0 star, you should send it out port 2. Now this rule is more specific, we'll say, than this rule because it has a longer prefix or a longer path through the tree. So we'll keep track of this as our last match now. So cross this one off, and we have a new rule that says if you match 1 0 star, then we'll send out port 2. And we'll keep going. Last bit is a 1, so we come to this node. There's no rule here, and since we've reached the bottom of the tree, then we're done. So now we look, and we see that our last match we found was sending out port 2. So this is the match we take, and we send it out port 2. So this is how the router uses the tree to figure out where to send a packet. First, it populates the tree with the entries in its routing table in this format, and then when it receives a packet, it walks down the tree, keeping track of the last match it found. And once it reaches the end, that last match is the one with the longest prefix, or the longest path through the tree, and so that's how it determines where to send that packet. Now, one problem that we like to ask you about in terms of longest prefix matching is, given a routing table, find a more concise representation of that table. So what that means is, if you have a routing table with, let's say, 5 entries here, can you find a way to represent that table with a smaller number of entries that still accomplishes, or that still has the exact same functionality? So all packets will be routed the same way, just that it requires storing less actual state, less data, in order to represent that table. So one nice way to solve these problems is to first build a tree out of the table. Because a tree is a good way to visualize all of your routes and then figure out, based on that, how you can sort of combine routes together to end up with a smaller table. So let's take the tree that we've already constructed from this example. Now, we want to be able to take some of these routes and then merge them together in order to get a smaller table. The only way we're going to get a smaller table is if we can take some of these routes here and combine them together. And the structure of the binary tree helps us out a lot with merging different rules together. Now, one question you might have is well, where do I start actually trying to merge these rules together? Which one should I pick? There's really no general way to solve these perfectly every time. Usually you just have to maybe try a few different ways to see what works, do a little experimenting. But there are some tips that you can try that will generally give you a good answer, or at least a great way to start off. So one thing that I recommend trying first is to start with the rules, or to start with the port that appears most commonly. So look at all the rules, figure out which port appears most often, and see if you can find a way to combine those together. So I'm going to write that down. So one tip is to start with the most common port. All right, so in this example, this port 1 appears 3 times. It's the most common port, so let's start with port 1. Now, in this tree, what you want to do in order to combine rules is to figure out ways to take rules and propagate them up the tree. So let's try these 2 rules here. We have one rule 0, 0, 0 that says forward out port 1, and one rule that says 0, 0, 1 forward out port 1. So we can try taking these rules and propagating them up the tree as far as we can. So for instance, we could move these 2 rules up to this open spot here, right? So what if we created a rule that said, if you match 0, 0, send it out port 1, right? Because either if we send it out 0, 0, 0 or 0, 0, 1, or if a packet matches either of those rules down here, we're just sending it out the same port. So why not merge that rule into just 0, 0, and then we don't care what comes after. So now what we've done is we've taken these 2 rules and we've merged them into one. And let's keep applying this process. So we'll keep trying to take our most common port and propagate it up the tree as far as we can. So you take your most common port and you propagate up. In order to merge your rules. All right, so let's continue. Now, in this tree, we see that we now have 4 rules, and each port appears the same number of times, twice. Right? So now, which one do we pick? Well, when you get to a point like this, another tip I would say is try to find the port which has like the most free space above it, where there's no conflicting rules above it. So for instance, this rule, P1 here, if we follow it up the tree, we can see that there's no other rules that we conflict with. Same with this rule for P2. There's no other rules it conflicts with. But this rule P2 here, if we go up the tree, we see that it sort of conflicts with this rule P1. So this one is going to be harder to propagate up. So instead we'll try the ones where we have free space to move them up the tree. So another tip, I would say try rules with the least number of conflicts. All right, so let's take this rule. So since P2 has a conflict here, that means that the rules for port 2 might be a little harder to propagate up. But the rules for P1 might be easier. So let's try P1 first. So let's take this rule P1 and just propagate it up. We don't even have to think about what we're merging it with at this point. Let's just try propagating it up the tree. So because there's no conflict here, we can move this rule up to this node here, just the rule 0 star star. Right? So what that says is if a packet matches where the first digit is 0, then we'll send it out port 1. Now you might say, well, wait, what about this packet P2? Because if a packet matches 0, 1, then it also matches the first digit being 0, right? But remember that this is longest prefix matching. So we will always take the route that is at the deepest level in the tree that we come across. So these rules will work out fine. So this rule, again, we have free space above, so let's keep moving it up. So let's move P1 all the way up to the top here. So now we have a rule that says for any packet, the default, the first rule that you come across is send across port 1, right? And this works because there were no conflicts in the tree as we were propagating that rule up. So this is totally fair game for our routing protocol. Now let's keep trying to propagate rules up. So let's go with this rule P1. We see that we can merge it with this rule up here. So I'll just get rid of this one. And merge it into this rule. So now we just have one rule that says any packet, you first match sending it out port 1. Then we have, so now we're left with just this P1 rule at the top and these 2 rules for P2 at the bottom. Now, if you want, we can propagate these 2 rules up, but it's not necessary because we can see that at the top of the tree there is just a single rule for P1. And neither of these rules, we can't combine either of these rules with each other because there's no way to combine them at some point up the tree without hitting this conflicting rule. And this is just the top of the tree, so there's nowhere else to go. So this is going to be the total number of rules that we'll end up with in the tree. So if we wanted to write out our new, more concise routing table, actually I'm going to use a red pen. So what we would write is first this rule for port 1, we call it just star. Or you could say star, 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 but this is our default rule that every packet will initially match. So all packets, the first rule is send it out port 1. Then, if you have packets that reach these specific rules for port 2, then we need to send out port 2. So these rules correspond to 0, 1 star, port 2, and 1, 0 star. Right? And this is our final answer. So by taking these rules and propagating them up the tree, we were able to take our routing table that had 5 entries in it and convert it to a routing table that only has 3 entries. So we found that we could accomplish the same routing functionality in much less data. Alright, so now that you've gotten your feet wet with longest prefix matching, let's try a more challenging example. So now I've changed the ports to represent the problem from discussion 5, problem 4, and I marked the changes from my previous example to the discussion problem in green, just so you don't get confused because they are pretty similar. So go ahead, take a minute, pause the video, and mark out these rules onto this tree. Alright, hopefully this is the answer that you came up with. So we have 0, 1 star corresponds to port 1, that's this node right here. 0, 0, 0 corresponds to port 2. 0, 0, 1 corresponds to port 1. 1 star star is port 2 here. And 1, 0, 1 is port 1 down here. Alright, so now that you have your binary tree laid out, it's time to try and merge some ports, merge some rules, and see if you can get a more concise representation of our routing table. So go ahead and take a minute, pause the video, try to work this one out, and remember the tips I've given you. So try to start with the most common port and propagate it up as much as you can. And also try the rules that have the least number of conflicts above them. See if you can propagate those up. So take a minute, try it out, and then we'll talk about it. Alright, let's see if your answer matches mine. So, by the way, I wrote up the binary trees twice on the board here. And that's because I'm going to work through this problem 2 times. First trying port 1, and second trying port 2, and seeing what happens. So, let's start with following the rule that says, start with the most common port. So in this case, port 1 is the most common. So there are 3 of the rules. Let's see if we can try to propagate those rules up. So we'll look at our binary tree, and we see we have a P1 rule here and a P1 rule here. Now, can we propagate these rules up? Yes, we can, because there's no conflicting entries here up the tree. So we can take these rules and propagate them up as far in the tree as we want. So let's move them all the way up to the top. And create this rule here. So we've taken these 2 P1 rules, propagated them up to the top of the tree. And now we have a route that, or now we have a rule that all packets initially will match that says send out to port 1. Okay, now we have a rule, port 1 down here, 101. And this rule conflicts with this rule here, the 1 star star that says forward out P2. So can we propagate this one up the tree. Let's say we want to propagate this rule up to this node here. Can we do that? Take a minute, think about it. So the answer is no. We can't propagate this rule up. And let's see why. So if we were to change this rule and propagate it to here, we've created an issue because of this conflict it has with P2 above it. So for instance, what if the router were to receive a packet that had the ID 100? Okay, so in our binary tree now, what we would do is we would walk down 1, 0, 0, and we'd get here. Now, what's the last rule we match if we go down this tree? Port 1. So that would say forward this packet out port 1. But what's the problem here? Originally, this packet would have gone 1, 0, 0. It would have matched P2 first. Then here, there was no rule before, right? It was just this P1 down here. It would go 1, 0, 0. It wouldn't match any other rule, so it would take port 2. So by propagating this port 1 up, we have modified the functionality of the routing table. And that's not good. We can't do that. So we can't propagate this P1 up. So P1 has to stay down here, okay? So this is something you need to be careful about when you are propagating rules. If a rule has a conflict with another rule about it, you have to be very careful about merging rules and propagating them up. Now, just for fun, if this node happened to have a rule of port 1, would we be able to propagate these rules up now? Think about it. Yeah, we would in this case. Because this node, whatever packet reaches this node, then no matter what comes after it, it definitely goes to port 1. So we can merge these two rules together here. So this is okay. So always be careful when you're merging routes. Let me write that as a note. So just always be careful of conflicts. All right, and that sort of goes in line with this rule too, which is try the rules that have the least number of conflicts. So generally you want to avoid merging things that have conflicts at first. And yeah, just be careful that you're not changing the functionality of the table. Okay, so now we're back to the setup of our table currently. Now, we have this rule P2 here and this rule P2 here. Can we move either of these rules up and try and combine them? No, we can't, right? So for this P2, it's pretty simple. We have a direct conflict here, so there's no way we can propagate it up. But for this rule, P2, if we tried to move it into this node here, we're going to run into the same problem that we ran into with this P1, where if we tried to create a rule P2 here, then we're changing the functionality of this node here, which used to have a rule port 1. So we can't move P2 up. So at this point, we're done, and our routing table will have 1, 2, 3, 4 entries. Now, can we do better than 4 entries? So let's try this binary tree. See, I will stand here. Let's try this tree. And now instead of starting with P1, let's try starting with P2. So with P2, we have nodes here, or we have rules at this node here and here. So 1, star, star, and 0, 0, 0. Now, can we propagate these P2s up? Yes, we can, because there's no conflict above them in the tree. So let's move this P2 up, and we'll move this P2 up, and we'll make a new rule at the top of the tree. Okay, so now we have P2 as our star root wildcard. Everything matches originally. And then now we have some leftover P1 routes. So let's see if we can merge or move any of these up. So first, let's start with this P1 here. Can we move this P1 node up to here? No, we can't. Because if we did, we would change the functionality of this node here. Because this rule is no longer here. We moved P2 to the top of the tree. So we have to be careful that we don't take over this branch. This branch still has to belong to P2 because of this rule. So we can't move this P1. What about this P1? Can we move this one? No, we also can't, because again, if we moved it up here, we would be changing the functionality of this branch, which we can't do. So P1 has to stay here. What about this last one? No, we also can't move it up, because if we took P1 and moved it here, we would now be saying that any packet that matches 1, 0 at least is going to be sent out port 1. But that is changing the functionality of this branch here. And that's not good, because this packet was originally destined for P2 because of this rule. So we can't move P1. So since we can't move anything else, then once again we're finished. And this has 1, 2, 3, 4 entries in the routing table. So either way, whether we started with P1 or P2, we ended up with the same answer. So it goes to show that these heuristics don't always work, right? Sometimes you're not always going to get a clean answer just by following a certain rule. Sometimes you may have to play around with the problem a bit, as I did here, but nothing great came out of it. So I hope this helped you with this longest prefix matching stuff and how to figure out shorter, more concise routing tables. If you have any questions, you can leave them in the comments below or on Piazza. Thanks for watching, and it is 2:30 a.m., so have a good night. See you in section tomorrow.
Being a craze to an entire world order.
Constant trading is not only distracting kids from classwork, but turning the playground into a black market where they buy and sell rare cards.
The children are developing relationships with all these Pokemon.